So in these examples, we're going to work some work problems where it's the spring application. So Hooke's law, compute the work required to stretch a spring from equilibrium to 13 centimeters past equilibrium, assuming that the spring constant is K equal to 50 kilograms per second squared. So first thing that I want to do is I want to convert 13 centimeters into meters, which is 0.13 meters. Okay. Then I want to use the work formula, which is the integral a to b of kx dx. Okay, this is for the Hooke's law. Okay. Now, the kx, this is my force function. So for this one, my spring constant is told to me. I don't need to do any work. It's just 50 x. All right, and I'm taking the spring. So this is at its natural resting equilibrium, and then I'm going to stretch it 13 centimeters past that equilibrium. So I want to know what's the work to move it from 0 meters past to 0.13 meters past the equilibrium. And it's 50x for my force function dx. Integrate this. I get x squared over 2. Dividing 2 into 50 gets me 25 from 0 to 0.13. And evaluating that, I have 25 times 0.13 squared minus 25 times 0 squared equals 0.4225 joules. Okay? So in your homework, maybe it's going to be like, it's going to have like a box, and then there's going to be a J out to the side, and you just put the 0.4225 in there, or however many decimals it says to round to, if it does specify. Okay? Remember, work, joules is the units for Newton meters. Now compute the work required to stretch the spring from 4 centimeters to 16 or 15 centimeters past equilibrium. Okay, so we take our spring here, and I'm going to stretch it from, what's the work from a 4 centimeter past to stretching it to be 15 centimeters past. Okay, so I want to know how much work was done in this place right here to go from this spring, stretching it out to get to this spring here. Okay, first thing I do is I convert my centimeters to meters, so 0.04 meters, and 15 centimeters is 0.15 meters. Okay. Now the spring constant here, I'm told, is K is 200. So that means my force function is Kx for Hooke's law, which is 200x. So the work required to stretch from 4 centimeters to 15 centimeters past equilibrium, that's this part right here. That's going to be the integral from 0.04 to 0.15 of 200x dx. Integrate this, x squared times 100, evaluated 0.04 to 0.15, gets you 100 times 0.15 squared minus 100 times 0.04 squared, and this is going to be 2.09 joules. Okay? So hopefully this kind of gives you an idea, better understanding on how to compute the work using Hooke's law here.